Hey everyone, welcome to the fifth episode of Distributed Systems 101 series. We will be talking about transactions here and the strong level isolation which is provided by the transactions. So in the previous episodes, I believe we have covered replication, and in this one we will cover transactions. So let's quickly start with what is transactions actually. So I'll quickly write it down here. So what are transactions? So basically transaction says that if you have multiple operations which needs to be taken place or which needs to happen synchronously or in a sequential fashion, then you can wrap them around in a transaction, meaning that they can happen sequentially and supporting the atomic nature, meaning that if any of the operation gets failed or like is not able to happen, then all the rest of the operations which are present in the transaction will gonna fail, right? So suppose if I say here that suppose we have a couple of operations, let it be read, write, again a read operation, and then another write operation, and this needs to happen sequentially like this. So suppose we wrap all this here in a suppose we wrap all this here in a form of a transaction, and we call this transaction as T1. Now in that case, what transaction ensures that all these operations will hold the atomic nature, right? So the transaction will make sure that the atomicity of this operation or a collection of operation is maintained. Now what do I mean if I say atomicity here? So what I mean is that suppose this transaction uh, it starts with a read operation. Now the read operation got committed successfully, and now it goes to the write operation which also got committed successfully. Now it goes to this read operation, and it seems that this operation failed due to some reasons, like might be some machine issues or might be some database connection problem, but due to which this read issue failed. Now what will happen is that if this was not a part of transaction, then these two operations would have persisted or would have not been rolled back. So what would happen is that if we perform this entire operation again, then these two operations would have been performed twice, and we don't want that. So in order to keep the database in a consistent state, what a transaction does is that if this read operation fails, then at this point it gonna start the rollback procedure, right? It starts the rollback procedure. By this, what it means that all the operations which has executed before this particular R2 read operation, all of them will get rollback. So this operation was executed, this will be rollback. This operation was executed, but this is a read operation, so we don't need to do a basic rollback here because it's already a read operation, so we don't care much here. But yeah, but for the write operation we will perform a rollback so that our database stays in a consistent state. Like basically this our database is returned into the state where before the transaction has started. So it returns to the state before the start of T1. So this is what a transaction guarantees. So a transaction also avoids multiple discrepancies or multiple race conditions from happening into the system. So we discussed that a transaction can wrap multiple operations into a single entity, making it atomic and isolated, right? So due to this particular nature, the transaction also avoids multiple unfortunate scenarios or race conditions from happening into the system. So one classic thing which a transaction can avoid is basically if the multiple clients are writing to the same data. So if multiple clients are writing to same data, then it avoids one client overwriting the other, right? One client overwriting the other. What does it mean is, suppose a transaction is happening, right? A transaction T1 started by a client C1, right? It started the transaction, and within this transaction we have a couple of write operations. So suppose we have three write operations which was performed on a data item X. Now, what if a client 2 tries to perform a write, suppose a third write on data item X? Then if this transaction is currently in progress, then it will not allow other clients to perform a write operation while this is happening, because if this write operation is happening, the transaction, if this transaction is taking place, then it will not allow another client to perform the write on the same data item, because it can lead to data inconsistency. So that is one thing which a client avoids. So this particular scenario avoids multiple race conditions, right? Sometimes the transaction can also avoid other client to read from the data item. So again, if another client says C3 tries to perform a read, right? Suppose try to perform a read on a data item X, right? So if this transaction is taking place, then it will not allow the client to perform a read operation over it as well. And why it does not? Because while the transaction is happening, the data item X is going through a series of writes, right? W1, W2 and W3. So it is not guaranteed that the data, what should be the value of that X be while being in the transaction T1, right? The value could change during the series of write operation, and hence the client, the data item, the value of the data item is not fixed right now in the middle of the transaction, and that way it will not allow another another client to perform a read operation on top of it, right? So that is one thing which a transaction avoid in order to maintain the data consistency, or in order to maintain any race conditions within the clients, right? Now this, like, with transaction comes multiple performance issues as well. So now transactions can cause multiple performance overheads as well. So we discussed previously that transactions can allow a user to follow an atomic nature, right? So basically what I wanted to say is that a transaction makes sure that multiple of operations, a series of operations which are performed under it, are atomic in nature. And also transactions allow the operations to be isolated. So suppose if two transactions are happening, then it will make sure that the two transactions happen in an isolated manner, and those two transactions do not try to overlap each other or do not try to interfere each other, right? So these are the two things which a transaction offers. Now since it offers strict atomicity and isolations, due to this this can cause some performance overheads as well. Why? Because as we discussed in our previous example, multiple clients would have to wait to perform read or write on a particular data item who has already been taken uh, uh, in position of a transaction, right? So suppose if a transaction is owning a data item to perform a read or write operation, then other transactions or other clients who are trying to perform a transaction or perform a read or write on the data item has to wait, and that was the reason which caused the performance overhead. This is the time factor which we have to, like, sacrifice in order to maintain the atomicity and the isolation nature, right? Now this is basically a transaction performs, make sure that the asset property is maintained, and that is the whole reason the performance overhead happens. Now there are other type of systems as well that does not follow this asset properties, right? And they are called, like, they generally follow a base property, right? This is this has sometimes less overhead by sacrificing the atomic isolation, in consistency and durable acid nature. Yeah, by sacrificing the acid nature, they try to get a good performance, right? An improved performance over the classic acid properties. So basically base has an improved performance, right? And what base is, as the name suggests, it is basically available. It's a soft state and eventually consistent. Since acid properties make sure a strong isolation or a strongly consistent system, the base method performs a eventually consistent systems. So now before going towards the strong isolation scheme, let's discuss about the isolation properties a transaction can offer. So I'm going to quickly erase this. So we discussed atomicity previously as well in the previous part of this series, where we tried to look multiple operations happening in a transactions, and if one operation failed, then all the rest of the preceding operations also failed. Right, now we'll try to look at the isolation piece. So let's take a first example where we are not following an isolation, where there are two transactions which are happening, but they are not following the isolation nature, and let's see what problem can incur if that is the case. So suppose there is a transaction T1. This is a time series graph here. So we have worked on this time series graph multiple times in our previous episodes of this series as well. So suppose this is a data item X who has a value of 5. There is another transaction T2 here. So there are two transactions which is going on parallelly, and they'll try to update the data item, and let's see if the isolation state is not followed, then what will happen. So if this transaction T1 start here and it tries to read the data item X, right, then if it tries to read the data item, then it will get some value. So suppose it get a value of X to be 5, and it starts writing the value. Okay, now it starts performing this. Since it got the value of X, it starts performing a write. And what is that? It is trying to perform an increment operation on X. So it is nothing but, oh, just wait a second. Okay, yeah, cool. So it is nothing but a write operation here, right? So what it is trying to do here is it is trying to perform a write operation. It is nothing but it is X equal to X plus 1, a classic write operation. That's what it is trying to do. Now once the write is performed, the value of this X will be updated. That is, the value of X will be updated to 6. Now at the same time, the transaction 2 also enters and it tries to read the value, right? Now here we should look carefully that at this point of time the value of X is still 5, right? The value of X is updated to 6 at this particular instant of time. So at this point it will still, well, if a transaction reads, it will still get a value of 6, right? And since it gets a value of 6, this transaction also tries to perform a same operation of a plus plus, which is nothing but X equal to X plus 1. Now the problem here is that it also performed the write operation, and it, after writing, it tried to put that value to the data item X. Now it performed an increment operation, and it also saved the value of X to 6. Now after the end, like once these two transactions have executed, we got the value of X equal to 6. We started with 5, we got the value of 6. But if you look at a higher picture, we can see that these two transactions try to perform an update, try to perform an increment on the value of on the value of X, and after the execution of both the transactions, the value of X became 6 from 5. But this should not be the ideal condition, because there are two transactions trying to update the value of X. So ideally what should have happened is that from X equal to 5, by the first transaction it should have changed into 6, and by the second transaction it should have changed to 7. But if the client tries to query the value of X, he will see that okay, the value of X is still 6. There is some problem. The client will probably think that okay, one of the transactions might have failed. But here what has happened is that the transaction has not maintained the isolation nature. Now if the transaction would have isolated, or it would have maintained the isolation property, then the transaction 2 would not have been allowed to read the data item X at this point of time while this transaction was executing. So this was the time frame where the transaction T1 was executing, right? So during this frame, the transaction T2 would not have been allowed to read the value. Since we are allowing the transaction T2 to read the value of X, right, in the middle of a transaction, that is where we are violating the isolation property. So let's in the another example, let's see if we maintain the isolation property, or if we follow the isolation property, then what will happen here, then how this entire picture will make sense. So I'll just clear this up. Okay. uh, let's look at another example where this transaction will perform will these two transactions will maintain an isolation property. So now what we will do is that we'll do the same thing which we did earlier. So in the same manner, we'll be having like a 2 time series lines here and one data item x. Now the value of data item x is 5. We have transaction t1, we have transaction t2. Now what will happen is that transaction t1 will again try to perform a read operation on x, and it will get a value, right? Now it got the value of x equal to 5. Now what it will do is that it will try to perform a write operation. So write x plus plus. This is very similar what we did earlier, right? We performed a write operation. Now once the write operation has been performed, it will try to write the value of this into the data item. Now what it does is that it tries to perform a write operation here, and it will try to change the value of x equal to 6. Pretty simple. Took the value, read the value of x to be 5, incremented over the value, and changed the value of x from 5 to 6. Now the problem was happening here is that when the transaction T2 tried to perform a read operation here. Now here the issue is that in our previous example, we were allowing this transaction T2 to read the value of x in the middle of transaction T1. Now since this transaction is like started from here and it has like got committed here, in this point we will not allow any of the transaction to perform a read operation. So if we try to perform a read operation, we'll basically give an acknowledgement to the user that hey, this data item we are looking for is currently locked, so we can't allow you to read on it. So you basically have to wait for some time until the transaction T1 completes and release its lock from on the data item X. Now the transaction T2 complete at this point of time, right? So after this particular point of time, right, after this particular instant of time, if a transaction T2 tries to read the value of data item X, it will be able to read it successfully. So now suppose if at this particular point of time transaction T2 tries to perform a read operation on X, now then it will get a value of X to be 6 because it was updated previously by the transaction T1. Now since it got the updated value, it will perform a write operation, similar operation which we did earlier, write of x plus plus. After performing write operation, it will gonna write on the data item x, right? So basically the value of x will change to 7. Now you see how in the previous example these two transactions did not follow the isolation property, due to which the end value of x was 6, right? But it should have been 7 because the two transaction was performing a increment operation. But now here, since these transactions followed an isolation property, and you see that here at this point of time the transaction was not allowed to read, right? And here only the transaction was allowed to read once the previous transaction got committed. We got a correct value of x, right? These two transactions were performed serially or synchronously and updated the value of x to 7. Now let's look around some of the classic use cases where retrying a transactions might not be a good idea. So we discussed transaction, we discussed how it ensures atomic and isolation property, and we also discussed in atomic property that if a transaction failed, it can safely retry itself, right? Because it basically it overlaps, or it basically rollbacks all the writes which has been done previously. So it makes sure that the database is returned to a state before that transaction happened so that it can retry itself. But is it always safe to retry a transaction? Let's see. We'll see basically three cases where it might retrying a transaction might be a bad idea. So let's understand case 1 here. So case 1 is basically, what if transaction succeeds, right, but network call fails. So in this example, what can happen is that, suppose there is a client here and it is trying to perform a transaction. So we have a system here, right, which is, suppose we have a transaction here which can perform a series of writes. Okay, so let me clear this up here. It should be right. Okay, so it is performing a series of write and then it is committing itself. Basically the transaction is committing. So from here the transaction start, perform the two writes and it commits. Now the client sends the request here and this transaction initiates, this write is succeeds, this write succeeds, and the transaction is committed. After the commitment, the transaction sends an acknowledgement call back to the client saying that, hey, this transaction has committed and your request has been processed successfully. But at this point of time, there was some network issues or a network lag which causes this acknowledgement to fail or acknowledgement to not reach to the client. So at this point of time, the client does not receive any acknowledgement back from the system, and in that case the client might think that, hey, I haven't received any acknowledgement from the system, it means that my transaction must have failed, let me retry. So what it can do is that it can again perform another request to perform the same transaction, and in that case what will happen is that the client does not know that this transaction has succeeded earlier because it did not get an acknowledgement from the system, but actually in the system the transaction has already happened. So what will happen is that the transaction will occur or eventually happen again, and this will perform the same transaction twice in the database. So it might be the case that the database might be left in an inconsistent state or in a state which is not known to the client, right? So here in this case, retrying a transaction might be a bad idea. Now let's discuss the second use case. Here, what can happen is that, again, here in this case as well, retrying a transaction might be a bad idea. So here let's assume that okay, here let's assume that we suppose our transaction fails due to increasing load. Now this is also a very classic example. What can happen is that transaction might fail due to increasing load. So it is very simple. Suppose we have a transaction which can happen. We have a system which can perform a transaction where this transaction starts, perform a series of writes and gets committed, right? Let's see, it gets committed here. Now if a client tries to perform a sends a request to perform this transaction, and since this system is currently overloaded with a lot of requests, right, it's basically like overloaded with a lot of requests are coming, like there are a lot of clients. Suppose there are a lot of n number of clients which are trying to perform a request on this system, and n is a huge number, right? N is a huge number, and all of these are trying to perform their request on the same system, due to which it is getting overloaded. Now since the system is overloaded, the transactions are failing, right? Suppose some of the transactions are failing. Now in that case, if the transaction of some of the clients fail and they try to perform a retry, suppose they say that, okay, the transaction is failing, then ideally I should make a retry. Then the transactions fail and they retry, and if there are a lot of clients and they again try to retry the same transaction on the system, then what will happen is that we are not solving the problem. Ideally, we are making it worse. We are making the use case worse by increasing the load, right? So instead of solving the problem by retrying, we are increasing the load of the system and allowing more and more transactions to fail. So it can like trigger a domino effect where retrying a transaction can cause more load on the system and it cause more transactions to fail, which can again cause some retries, again increasing the load, causing more and more transactions to fail, and might at the end your system might go down. So that is a classic example where, so this is basically a case 2. So this is basically a case 2 where retrying a transaction might be a bad idea. Okay, now let's look at the case 3. I'll quickly erase this up. Now let's look at case 3. So case 3 is basically if a system is performing some external operations, right? External operations performed by transaction, which ideally cannot be rolled back. In that case, retrying a transaction can be a bad idea. Now let's say we have a classic example of a transaction T1 which performs a write, and along with a write it also triggers an email to a bunch of users. So we have a group of users here which are basically the recipients of this email, and once the email is sent, the transaction commit itself. Now what can happen is that if in this particular scenario, if this transaction at any point fails, then we can roll back this write operation, but we can't roll back this email trigger operation, because the email has already been sent to a group of users, right? So we can't roll this back, and if we retry it, then what will happen is that this email will be sent twice. Like it will be sent twice to the group of users, which might cause confusion. So this is a third case where retrying a transaction would be a bad idea. Now in this case we might get away with it by, if we're trying to perform an rollback, then we can maybe send a rollback email or an apology email to the group of users saying that, hey, the previous email which has been sent, please ignore it or please don't acknowledge it. So that can cause some damage control, and we can maybe safely retry the transactions. So we discussed about transactions. Now quickly understand the read committed scheme. So it is basically a strong isolation level scheme, which we also call a read committed scheme. It's one of the strong isolation levels which can be guaranteed by a transaction. And what a read committed scheme is, so basically what a read committed scheme is, it basically guarantees that there should be no dirty reads and there should be no dirty writes. Now what does that mean if I say no dirty reads and no dirty writes? Now to understand this, we need to first understand what are dirty reads and dirty writes, and then we'll see that the read committed scheme will not allow these in their transactions. So let's quickly understand the concept of no dirty reads, or let's first understand what dirty reads are. Okay. So what are dirty reads? So basically, by definition, what dirty reads is, if another transaction is able to read a data item which is held by a transaction, and another transaction is able to read that data item in the middle of the transaction, then that particular read is called a dirty read. So we saw this example in our previous use cases in the time series graph as well. I'm going to explain in a very quickly again. So suppose if this is a transaction and it's the data item X, right? And if this transaction is trying to perform read and some writes on this data item. So suppose if this transaction from this point of time to this point of time, this data item X is held by this transaction T1, and if at that point a transaction T2 can perform a read on this data item X and successfully get a particular value, which was the value of X at that particular point, then this is called a dirty read. Now this particular thing, this particular concept, this is called dirty read. This should not happen. We should not allow the transaction to read a data item, right? Read a data item in the middle of another transaction, holding it. Right? This is the concept of dirty reads. This is the thing which which a read committed scheme avoids. Okay, let me move this up here in the corner. Yeah, this is better. Yeah, so this is the thing which uh, read committed scheme avoid. Now how does it avoid it? Let's look at it. So again, I'm gonna draw a very similar diagram here. Very so suppose there is transaction T1 which is going here like this. There is a data item X with a value of 5, and there is another transaction T2. Now, what a read committed scheme says that there should not be any dirty reads. By dirty reads, we mean that if this transaction tries to perform some activity on this data item X from this to this point of time, right? So suppose this transaction starts here and gets committed here. Now, if at this point of time, if my transaction T2 perform a read operation, right, tries to read the value at this point of time, then two things could happen. Either the system says that okay, the data item X is currently the transaction T1 has currently taken a lock on the data item X and you can't read it, or what a system can do is that system can provide a old value, or basically the value before this transaction T1 even started. Whatever the value of X was, the system can return that value. So here what a system can do is that okay, you want to read the value of X, here is the value of X is 5. So what the value transaction T2 received? The transaction T2 received the value which was before the transaction T1 acquired the data item X. So transaction T2 received the value of X which was before T1 acquired a lock on it, right? So it got a value of 5 instead of getting any intermediate value what was assigned to X at that particular instant of time. So this is what can happen in a dirty read. We understood the dirty read concept. Now we will gonna understand what are dirty writes. So let me quickly write here. So this is very similar to dirty reads. What dirty write suggests that if a particular data item has been locked or has been in process by a transaction and it is currently in an uncommitted state, then any other transaction cannot perform a write on top of it. Meaning, suppose let me draw the time series graph again. Suppose this is a transaction T1 and this is a data item X here. Okay. Now, if a transaction T1 took a lock on data item X at this point of time, and now here it is performing some operations, right? And at this point of time, the transaction committed, right? At this point of time, the transaction started, and this point of time, the transaction committed. Now, during this phase, right? During this phase, if a transaction T2 comes up and tries to perform a write on data item X, then it should not be allowed to perform a write on it, because at this point this data item X is in an uncommitted state. Is currently held over by a transaction T1 which is performing some operation on it, and it will commit at a later stage of time. So at this point of time, the user will not be allowed to perform any write on this piece of data item. So basically in this phase of time, if a transaction comes up and asks to perform a write operation, we will not allow the user to perform any write on it, right? This is the no write area. So the transaction cannot perform a write here. Now what can happen is that transaction maybe comes up at a later point of time and it can perform a write at this stage of time, and at this stage we will allow the the transaction to perform a write if this data item is not held by any transaction. So that is basically the concept of dirty writes. We discussed dirty reads and dirty writes, what dirty read is and what dirty write, what both of the concepts are. Now basically what read commit makes sure that there are no dirty reads and no dirty writes. Now you can easily understand what a read committed scheme is, since we already have an idea about what a dirty read or a dirty writes are. So it makes sure that there are no dirty reads and there are no dirty writes. And how it does make sure about it is by acquiring locks on the data items. So we saw previously that if a transaction is trying to perform some operation on data item X, it tries to perform a lock on top of it. It locks that particular data item so that no other transactions can perform a read or write while the earlier transaction is executing, and only once the transaction has committed successfully, it releases the lock from the data item, and then other transactions can perform their operation or acquire their lock on it. Now this is the read committed scheme. This is a part of a strong isolation levels. In our next episode, we will discuss weak isolation levels. So you saw that this strong isolation levels can cause some performance overheads because there are a lot of restrictions which they apply, right? They apply a lock on the data item, and during that no other transactions can perform any operations on top of it. They all have to wait, right? So that is the cause of performance overhead here, and we'll try to understand like the weak isolation level in the next episode, and we'll see that how they can maybe perform a better and they can provide a better performance as compared to the strong isolation level schemes.